So hi everybody, I'm Dimitri Fontaine. You might have run into me the previous days, and maybe you were at the tutorial before. We're going to talk about PostgreSQL for developers, and the whole goal of this talk is, so how many of you are actually developing application against PostgreSQL? So good bunch of you, good. The aim of the talk is, if you're not doing it that way already, maybe you are, maybe you're not, to make you rethink the way you use SQL in your application, and consider that SQL actually is a nice programming language meant really for processing data and not just serializing it and getting back together in the application. You can actually process the data in SQL, and so this whole talk is about that. So I'm Dimitri. I work at Second Quadrant, and I've been doing some PostgreSQL work around the years. The most recent project that I'm publishing now is pgloader, which allows you to transfer data, to load data, whatever it is, into PostgreSQL. So we support sources such as SQLite, MySQL, CSV, fixed with files, DBase files, and IBM, IXF files, and plenty of stuff. So if you need to load data in Postgres, check it out. It should work for you. So let's get started. I took the liberty to consider that most developers nowadays are maybe working on the web. So the stack you see on the slide is oriented towards those developers. Maybe you're not doing that, but don't be offended by it. It's just an example. So if you're doing web development nowadays, you already have to deal with different kind of technologies and languages. I skipped completely in the slide the backend language because some people do Java, some people do Python, some people do PHP, Ruby, whatever. Each time there is a web application, you still need to do some HTML, some JavaScript for the front-end application. JavaScript maybe means jQuery, and on the backend side of things, you do some SQL too. So would you say that SQL is more like HTML for your application development process, or more like JavaScript or jQuery? We will see that for me, and I hope that if it's not the case still yet for you at the end of the talk, SQL is really meant to be compared with JavaScript, not with HTML. Okay. So to get there, let's take a really simple application example. So there is a counter that only ever increases over time, but sometimes you get back to zero. So for example, it could be like the network bandwidth that you see when you do ifconfig on the network device, and that keeps getting up, but if the virtual machine gets rebooted, or maybe there's a bug, a kernel bug or something, you get back to zero and up again. So you have a cycle, a counter that ever increases but can have cycles. What you want to do out of that is being able to invoice the bandwidth usage to your customers. So our goal as developers, so someone gets to us and say, okay, we have the numbers, we have them in the database. Your task today is to prepare for the invoicing of the customers. So we want to have the number at the end of the month and know how much bandwidth has been used out of the counter. So it's quite a simple project, and we can do it together just in this talk. Well, maybe not the reporting parts and the nice UI parts and the search extra, but the basis. So usually the first thing that you want to spend time on in SQL is really the DDL, the data definition. SQL is a strictly typed environment, and any SQL query will get you back something that the type of has to be known before running the query. So the DDL is mighty important. Joe Selko said that 80% of the time when dealing with databases should be actually spent on working on the DDL. Like most of the query performances problem you might have in your applications, maybe you could see again at the DDL and solve them by having the right data structures in the first place. So mostly is that. So in that slideshow, in that presentation, though, we are not spending that much time on the DDL, as you see. So let's take a single table of measurements for our example with the date and the measure we got out of the counter that sometimes resets. That's simple enough. But I'm not, as you might have heard already, I'm not a native English speaker, and spelling out full dates is going to completely ruin the presentation. So instead of doing that, let's have just a tick. So rather than having a full timestamp, we have a tick that ever ticks. So the tick numbers are 1, 2, 3, 4, 5, extra. That's the time that goes on and on and on again. And for each tick, we take a measure. So maybe we tick each 5 minutes, maybe we tick each hour, whatever. We won't really care about that in the presentation. And that is an example of data. That's the first example, the first test we will fix to have the number at the end of the month. So that's another way to see at the same data. And so if we begin at the first tick with a counter that is 0, and then it ever increases up to 40, it means that when we reach tick 5, the customer actually did use 40, whatever it is, 40 units that we want to invoice to him, okay? It's not the sum of 10 plus 20, because we measure 10, and one tick later we measure 20, so we need to invoice 10 more. So if we have those numbers, then at the end of the month, we will invoice 40 plus 60. So we want to invoice 100 from that. Is that okay for everybody for the example? So that's the use case. Just on the side, if you're using PostgreSQL, maybe your application would better want to handle the data like this. It's really easy to do. So you have an array ag, that's an aggregate. So in the modern NoSQL world, they keep selling that, well, it's magic, they have map reduce. Well, in SQL world, we call that an aggregate, and we've been having that, for 40 years. So there is an aggregate in PostgreSQL that you can use to get the data as an array. And so if it's better for your application, just do that. So now, as many of you are developers actually, try to think about it. You have this data as input, and the output is 100. So you need to write some code to do that. It's not the most complex code you will ever write in your life, okay? But it's still some lines of code. So think about how you would structure that code in your favorite programming language. If we want to do it in SQL, we need basically what we want to have. You see, it's the 40 and the 60. We don't care about the other lines of data. So we need to write a magic SQL command here that will give us this data exactly back. So who knows how to write this SQL already? Cool. So the rest of you, you're in the right talk. So SQL did change in the past year. So it's like Unicode. We still don't use it properly, Unicode, but it's been invented in '92. In SQL, in '92, we had window functions. And actually, we got them in PostgreSQL 5 years ago or 6 years ago in 8.4. But 8.4 is the current oldest version allowed in production with PostgreSQL. So everybody in the room in production actually can use window functions nowadays. You have no excuse. And if you don't know what a window function is, basically that means you've missed on SQL a lot, and you need to get back to training to SQL and understand what it is, because it will change your life as an application developer. It will really do. So let's see why. The lead here is a window function. And why it is in a window function? Because we have an over clause. So what we say in the query is, please, for each and every line where I have a counter, I want to see the next value of the counter. And so that's lead. And the next value has only a meaning if you have an ordering of it, because otherwise next means nothing. It's just random. So you want to see the data in the window function ordered by the ticking, so that the next one is the value of the next tick. So for each line, you have the current value of the measurement and the next value of the measurement. So who knew you could do that in SQL, like see the next value? Yeah, okay, about the same one. So I will maybe stop the show and shows. So once we have that, it's quite easy to get to the next step, which is that we only want the 40 and the 60, so we only want to get to keep the value of the counter when either the next one doesn't exist here, because if the next one does not exist, it's null. It's because we reached the end of the result set. So that's the last value of the result set. That's the one we want to keep. We also want to keep all the values when the counter resets. And the counter resets when the next value is less than the current one. Okay? So if the next value is less than the current one, then I keep it. If the next value does not exist, I'm reached the end, so I keep it. In all the cases, I'm not interested, sorry. And that's it. So we have the answer here. And the trick is that as I'm using the same window function several times, so the same framing clause for the window function more than once, then I give it a name, and as I'm really good about naming, and I really don't want to confuse the next one who's going to maintain the query, I picked a really nice name, okay? So maybe you want to have real names when you do that. Another thing about the naming, so in this talk we are saying that SQL can be approached as code. So when you do code, you do commands. And it happens that SQL allows for commands. I don't have enough room in the slides to add in the commands, but in your own code, in your application, as soon as you do some interesting SQL, please consider that you are allowed to put any amount of commands in there. Okay, so that's code. So here we have the 40 and the 60. So now it's quite easy. So you see it's the same query again, but we just want to keep the rows where we have a value, actually, where it's not null. So the trick is that the window function here only applies last in the query. So the where clauses, the joins, the whatever you want to do in the query will happen first, and then you will be able to process the data in the window function frames. Which means that if we here wanted to put that query inside the previous one, the where clause here, we wouldn't have the result we wanted to have. And so the only way to do that is using a subquery. And the nice way to write a subquery in a modern SQL, there is some traps, but the nice way to write it is using a common table expression known as with queries. So who's new to the with queries? So okay, I won't expand on it. You just give a name to a subquery and then see from T refers to that. That's it. And so now we do the sum, and we have the number, so we can invoice the customer. So all we had to write basically is that SQL, that's 9 lines of SQL, and the problem is solved for the application. So I asked you before to think about it in terms of your favorite programming language. Do you think you could have done it in less than 5 minutes on 9 lines of SQL? Maybe you could, maybe you couldn't. But it's worth thinking that maybe the right way to do it was actually to write a single SQL query where you have the PSQL command line, which is a really nice feedback loop. So you begin with a really simple query, you add to it, you add to it, you have the right answer, put it in the code, and that's done. So really SQL is like code. 9 lines of code and the problem is solved. But, well, that was the first test. Maybe we have some more complex data, so let's add to it with, can you see that the reset cycle here? You go from 45 to 25. So it's a reset again, but we didn't see the 0. Of course, if you're measuring like the bandwidth on the network interface, you would be really lucky to exactly see the 0. So we need to test that our thingy still works when you don't see the 0. And well, yes, it does, because we've been careful enough to say that we want to keep the value as soon as the next one is less than the current one. We don't have the 0 hard-coded here, so it works. So this time we have 4 answers, and if we rerun the query, we have the right answer. Okay, so we can invoice the customer again. But now what you can see is that we are missing a where clause here to select the current month. In those examples, we're just saying that, well, give me the answer for the rule measurements that I have. So is it possible to actually restrict it to a single month? So let's do that. As I told you, it's important to do that one because the where clause and the window function clause might not behave exactly as you think it would. So let's see about that. Let's say that current month began on tick 4 and ended on tick 14. It's like you will be able to put real dates and timestamps in there if you want in your real application. It will behave the same. So let's just do the simple thing with the ticks. So the goal here is to insert the where clause into the query we had previously. So if we had the where clause here, as I told you, the where clause runs first, and then the result applies to the window function frames. So actually, it's pretty simple. There is no trick to be seen. We just add a where clause, and we restrict the dataset we see, and we have the answer. Well, there is a catch, actually. Because in that case, if the month begins with the measurement 30, you want to be sure you remove it from the result before you invoice the customer. You don't want to invoice the customer 30 units more than what it actually used this month. And doing that in the query turns out not to be as nice as one would want it to be. So you see that the first column here is that the first value we saw, which is here another window function. We saw lead already, and we also have first value. First value is give me the first value you see in the frame, and that's it. So that's simple enough. Now where it's not clean is that when we process the data out of this subquery, then we need to use aggregates because we want the sum of the max elements for each range before reset that we found. So that's okay. And we need to subtract the first value. And first here needs to be an aggregate too. But by design, the first value will always be the same for the whole set. So we apply the mean aggregate on it, and we have one of those rows. We don't care really about it. But so SQL is a little strange sometimes that way. Okay? But with that little trick, we can have the right answer to invoice the customer again. So it's not that complex. Now, as we are doing like nice SQL, let's get more complex in the query. What if someone goes to you and say, I think I have a problem with that particular counter or maybe that particular virtual machine where it keeps resetting and resetting and resetting again. I want to study the reset behavior of my counter. I want to see how many times per timing it will reset actually. So can we explore the data together and see the reset behavior of the counter? Well, it's a little tricky. So the top query here is the one we've been working with from the beginning of the presentation, so no surprise. The bottom one is meant to partition the data into cycles before reset. So maybe we want to see the result of the query before explaining it. So here is the result. The result is that we have all the ticks, all the values of the counters. For each value of the counter, we only keep the max if it's the last value from the reset cycle. And we want to be sure that for every value in the same reset cycle, we have the same number as the partition P. And in the query I edited, that number is actually the last tick of the range. Okay, so you see what is happening in here, right? So let's get back to the query. Given the first result, we're going to fetch, you see from the top table here, we're going to fetch the next tick where the max is not null. Limit 1, so that's the next one. So if we get back here, where max is not null, when you start from here, that's the 5, and every one of them has the same value. But then you want the next one where max is not null, so now it's 9. Okay? So let's improve on that. So all the queries up to now, you could copy-paste if you have the table definitions and some data, but you have that in the slideshow. So you could copy-paste them as they are on the slide directly in PSQL and see what happens. Starting now, it's not possible anymore because I don't have enough room on the slide set to show you the whole query. So in how do you call that in English? Brackets something. So in those brackets, I just have put enough context so that you can imagine what is the actual query. If you copy-paste that in PSQL, it will spit back at you that it's not SQL. So you need to do the copy-paste. So with tops as the usual query we've been using from the start, parts as the partition query we've just been using together the slide before. Let's derive the ranges. So the ranges are what? The ranges is from the first value of the tick to the last value of the tick. We did measure the maximum value over that window from the partitions, and we partition the data by the partition number we just did create in the previous query. And within a partition, as we want the first and the last value, we need to have a notion of the ordering, so we order by tick. Okay, so window functions allow you to use frames, and the frames are basically when you want to understand window function, the only thing you need to understand is the framing, which is which data the window function is allowed to see and in which order. That is all about it. The rest of the window functions, it's exactly like an aggregate, but it runs differently, and you can have different framing within the same query. So here, the framing we have is by partition, which works a little like a group by, if you want. And the result is that we see here that starting from tick 1 to tick 5, we did consume 40 measurements, 40 units. 6 to 9, 60, 10 to 14, etc., etc. So now we have basically we have the behavior of the counter with respect to its reset cycles. Let's go a little. Let's do more with that, because we're using PostgreSQL, so it's awesome. We have ranges in PostgreSQL. So rather than saying it's from 1 to 5 in 2 different columns, and then you have to write between clauses and remember that the values in the between are actually not in the query but in the table, so it's not written as usual. Well, it's called a range in PostgreSQL. If you have both the start and the end element of the range in the data, well, use the range data type. So here we build a range of integers with the same data as in the previous query. And here is what it looks like. So we said that from 1 to 5, we did measure 40. And when you use the range solution in PostgreSQL, here we're telling Postgres it's an inclusive range. But when it's printed out, PostgreSQL will print it out normalized. And the range of integers is a discrete range. And when it's normalized, the ending point is not included. That's just the way apparently it should work in English. In French, we don't do it the same way at all, but okay. So we have the ranges here. And so why did I want to have the ranges? So let's say that the fraud department or maybe the marketing department or someone is calling you and saying, you need to figure it out in the data. We have some strange case, the 11th of the month. We have a strange reset behavior, and I think the invoice is wrong because of that. Can you check this, please? So given that query, you just add, I want the range that I just computed to contain the 11th tick. So we knew that liter operator range containment already. Some of you, cool. So we want to see oh, sorry, that is in French. We want to see the counter behavior where the reset around the value 11. So we don't know when the cycle started. We don't know when it ended, but we want to find that out. And we also want to find the value that we want to invoice within that precise cycle. So that is this query. You run that query where the range actually contains the number you're after. And so it started on the 10th, finished on the 15th, and you invoice 45 units. Again, one simple enough SQL query. Well, simple enough. It does not fit on the slide anymore, so maybe it's not that simple actually, but you get the idea. It's just one SQL query. The nice thing about those kinds of queries is it's kind of hard, really, to come up with that query from the first editing session. Nobody writes that query in one go. Nobody does that. So if you want to do that, don't try it that way. That won't work. What you do is exactly what we did together here. You start with a really simple query, and then you add some things to it, then you add some more, then you continue adding to it, up until you get to the right query that you're interested into. And obviously, we don't have time for that, so I didn't show you how many queries I did type that were not doing what I wanted them to do. So everybody happens to do it that way. So it's normal to type in queries and after a query that won't do what you want up until you get to the result. The only way not to do that is to think hard about the problem. And apparently nobody wants to do that. So you try, it fails, you try, it fails, you try, it works. There you go. So maybe after you want to think about it to be sure that it works actually, and you were not just tired of having failures. But the way to do that with PSQL is really nice because you can you have the editing loop that is really instant feedback. So if you try to integrate that query from the get-go directly within your code, I think you will fail. But if you actually do it on the PSQL prompt or pgadmin something or whatever you're using, I prefer PSQL because of the feedback loop, but pgadmin is good too. You do your thing, and up until you have the right query. Again, why I'm spending time on telling you about that is because I'm trying to convince you that SQL is actually code. And if SQL is actually code, then you need to have a process for using it that looks like a process that you would use to write code in the first place. So we have a test case to begin with, and then we write the query until we reach the test case, and then we can integrate it into the application code, as usual with code. Any questions so far? Good. So now that we have been expanding on the first example, I wanted to show you some other use cases. So for those of you who were at the tutorial the other day, it will be back again to the same example you've already seen. I'm sorry about that. For the other ones, I wanted to show you some extending queries with PostgreSQL and some of its extensions. Because that thing here, the operator, or the containment operator, is only one of the magic things that you can do with PostgreSQL. There is way more to that. So let's see some other interesting data types and extensions. We've been spending time on window function and common table expression, the with queries, and we skipped the nice timestamp with time zone data type that we have in PostgreSQL and used integer instead with ticks because it makes it easier for me to do the presentation. But actually, when you use PostgreSQL in production code, what I think is the most interesting part of using PostgreSQL actually is its data type system. You can have advanced and rich data type in PostgreSQL that implements the behavior that is expected from the data type. And so you can offload that thinking from your application and just have SQL queries that work. And despite the data types being advanced, the SQL you will write still looks like SQL. So that's a little abstract. Let's see some examples. When you use PostgreSQL, you have plenty of extensions to use. Most of them come in the contrib package. So when you deploy PostgreSQL in production, be sure to ask your admins, or if you are actually the admin, do that. Install also the contrib package. Most of them are really, really nice and things you wish you had the day you want to use it. So install it. By default, it will change nothing in your PostgreSQL installation up until you do create extension something. That's the point where it gets activated, if you wish. Until you do that, there is no change at all. Just install the package. We have an extension, called IP4R, which is meant to host IP ranges. And as the name shows, it supports both IPv4 and v6. Okay. And it's not actually a PostgreSQL contrib, it's another project that you can use. And so everybody knows that an IP address, right, looks like this, but actually is a 32-bit integer. Okay, no surprise here. The thing with PostgreSQL is that if we load IP addresses into it, it will know it's actually a 32-bit number. So it will allow you to use the IP address that looks like this, and it will actually store a single 32 bits integer in your database, and it will be able to do some really fast lookups because it's only an integer. Here I've loaded, maybe you know it, the Geolite MaxMind geolocation database. So it's loaded into PostgreSQL with pgloader, obviously. And the Geolite gives you two columns that are integers that are the start IP and the end IP. So you could be loading the data as is. But in that case, we want to do something smarter about it. And so we load the data as IP addresses that looks like really IP addresses. And PostgreSQL is able, when given the starting point and the end point of the range, to derive the CIDR notation that you want to use actually. And once you do that, then you have an operator to check, well, to fetch the data that comes. So basically, how to read that is I want to know all the information I have for this IP. So find out which range it is in, and when you do that, then fetch me also the metadata we know about it. In the Geolite model, you have the blocks and the location. Blocks are what we saw before, so it's only an IP range and an ID. And then, of course, in your application, you don't care about the ID. What you want is actually the whole information, right? So what you want is actually, so that's an address. If you do a DNS lookup, host google.something, it's one of the addresses. And apparently, Geolite thinks it's in Mountain View, so it looks legit. The thing is that when using Geolite, they provide you with APIs to integrate it right into your C code or your Java code or PHP or whatever. But they will only do the lookup. They will not do the joins for you. So if you have metadata in your application database that you want to use after you've done the lookup, well, if you're using PostgreSQL, really, it is called a join. So you just join against it. So you're back to using good old SQL, where in input, actually what you did is a geolocation query. So who knew you could integrate geolocation right into your SQL code, like without thinking about it? Okay, so if you use PostgreSQL, that's the kind of thing you can do and benefit from. And so we have two things that we can see on the slides that are maybe not obvious on first sight. First is that it only took like less than 1.5 milliseconds to do that, and it was on my laptop. So you can actually use that in production, okay, for real. Usually when you do geolocation, you want to update a nice UI for your users, and Amazon said that if the UI loads in more than 20 milliseconds, they're losing money. So you want the whole application to be fast enough for your users. So it's important that this query that is offloading smart from your application and push it down the database, you don't want that to become a bottleneck. So it's important to check that. And given a running time of 1 millisecond and something, my guess is that it won't be a bottleneck. So you can actually do it and use it in production for real. The other thing that I wanted to talk about here is the location here. So again, when provided with the data from Geolite, what we have for the location is two separated columns, longitude and latitude. It turns out that PostgreSQL by default embeds a data type that is called point. And the point is a couple of floating point numbers that you usually use as coordinates on the globe. So given a geolocation request, we get back directly a point data type that you can use. So how to use it? For example, let's try to compute the distance in between the place you want to guide the users to when given his IP address, like where is the next pub, for example. So let's build that application. You have a smartphone, you have the map, the input you have is the IP address of the user, and you want to tell the user where are the nearest pubs, and you want to display the distance in miles. So if we have a table with the names of the pub and a position as a point, so point is the PostgreSQL data type that you will use in that case. Remember that the point is just a basic 2D vectors as you did in high school. It's not smart enough for computing the distances. For the distances, you need the sphere. You need to consider that the Earth is a sphere. So let's do that. So that operator here is default in PostgreSQL. It's the distance operator. So you get two positions, and PostgreSQL will compute the distance in between them. But it will do that like we did in school back in the day with just the vectors and arbitrary units. So the answer is an arbitrary unit. It's not useful as a distance to walk by, but you will still have it. And if you order by the distance and limit the number of results you want, then PostgreSQL will actually be able to implement that as what we call the KNN search. K here is 3, so that's the factor. And NN means nearest neighbor. So that's a K nearest neighbor query, which means like fetch me the nearest neighbors. And PostgreSQL will be able to do that with just an index scan and nothing else. So that's pretty cool. And here we fetch the pub names that are the nearest to that position. And for each pub, we get its position on the map. But that's not what we want to display. But the first thing, is that this query is a little slow. We said that by the Amazon rules, you have about 20 milliseconds to answer the customer before you're losing money on him. And the query is running in about 20 milliseconds. So it's a little, you don't have much time left to do the rendering on the application side. So maybe it's not good enough. But we said we could do a KNN search right into the index. So how you do that? Well, you create a gist index on the position, which is a point data type that PostgreSQL knows about. And now if you run the query again, it runs in less than 1 millisecond. So now you can integrate it into your production code. But we still don't have the distance. So let's work on that. To have the distance on the Earth, you need to consider that the Earth is actually about a sphere and do some complex computation. And the extension Earth distance has been made for that. It returns the distance in miles. So here you see that we have two distance operators. The first one is like less than, dash, greater than. That's the default distance operator that PostgreSQL uses and knows how to index. But that would give us like a vector-based arithmetic distance that has nothing to do with miles on the Earth. So we also use the less than, hat, greater than, that is meant to look like the other, but is different. And then we have the distance in miles. And so if you want to do a nice smartphone application, we just give the user where are the next pubs around him. That's a single SQL query. That's all you need. Well, I leave you to do the actual application, nice screens, etc. But for fetching the data, you do a single query, and there you go. And okay, so that one is not really needed, but it's seldom enough to have a use case for the lateral subqueries that I wanted to show you one. Lateral subqueries, the short story is that if you run that query before PostgreSQL 9.3, it will complain because, as you see, we are using the position of the pub name here in the same level of the join. So it will tell you, hey, you can do that. You cannot use a column from a table on the same join level. That has no sense. It's not join. Well, it happens to actually be a lateral join. And so nowadays you can do it, actually. So that example is just to show off the lateral feature. But what if, instead of having the smartphone and the geolocation of the guy, because you see in the previous queries, the data we have as input is the geolocation. So maybe your device is giving you that, but what if not? If not, what we do usually in the web is use the IP address of the device and convert that as a geolocation on the globe and then do the lookup. So again, it's a single SQL query. So the first query here will, given an IP address, fetch so the location as a point on the globe, and the second part of the query will give you the pub names around your location, and we want 10 of them this time, and erase the list of pubs with the distance. So either you're given the geolocation and you can use it directly, or maybe you're only given the IP address, and so you need to first do a geolocation query and then use the result of the geolocation query to actually find the pubs around the place. Well, it's a single SQL query. And it's not that complex. It's like, it fits in the slide, so it's like easy to embed in your application code. So what I want to take away from that talk is that actually you are using lots of tools already. If you're developing a web application, you have a complex stack of elements, and one of which is SQL. You're used to using plenty of tools, and SQL actually is a tool for coders. So it's like a development language. So maybe you want to consider SQL as a programming language that you use in your application. It's one more programming language. And, well, you're using SQL already, so make the best out of it. So that would be my conclusion from this talk. PostgreSQL is the SQL. Any questions? Yes?
So this question is about how to make a mind switch between an iterative approach to a declarative approach. Because like the first reaction I had when you asked me how I would do that is I thought about how telling it how to do it. Like, you know,
Yeah.
run over it, do this, pick this out. But I understand that you have to be declarative. I just want to understand how.
Yeah. So in case you did not hear, the question is about how to deal with the fact that SQL, even if it's a programming language, is not an imperative programming language. It's declarative. So what does that mean, and how do you cope with it? So it means that rather than trying to explain to the computer the solution you can think to solve the problem, you have to explain to the computer the problem you want to solve. So here in the query, there is nowhere in the query where we are explaining how to do the lookups. And we are only explaining that we want to find the location from the IP address and then use that to find the pubs around it. So we are still thinking of the problem we have, not how to solve it. So it's not what you're used to when you're programming. You are used basically to find the solution yourself and then explain the solution to the computer. But with SQL, you keep thinking about the problem and you explain the problem to the computer. Does that make sense? Yeah. So it's true that it's, I think it's called a paradigm shift. So it's not the same way to think as usual, but, well, it's really worth it. And once you're used to it, it's really easy to deal with it, actually. Other questions? No? So let's have a break.